This video talks about the first monolithic high-power voltage regulator designed by Bob Widlar at the National Semicondactor in 1969. This is a 3-terminals linear regulator providing a fixed 5-volt output with 200 mA or 1 amp output current. This bipolar device was housed in a TO5 or TO3 CAN package. In the late 1960s, many companies were designing IC voltage regulators and there was a perceived demand for a monolithic device. But the big problem was including the power transistor in the monolithic die with all the other circuitry. No one believed it possible, including Widlar apparently, who in June 1969 wrote a paper in IEEE where he laid out the case against the monolithic voltage regulators. Then, in February 1970, he presented another paper at ISSCC where he published the circuit of the LM109, the first monolithic high-power voltage regulator. The solution, of course, was his bandgap voltage reference, which allowed the reference to coexist with the wide temperature swings caused by the integrated power transistor. Reference circuits and linear regulators actually have much in common. In fact, the latter could be functionally described as a reference circuit but with greater current or power output. Voltage references have a major impact on the performance and accuracy of analog systems. Accuracy of the voltage reference is important, as well as temperature drift and noise. Here you see the simplest voltage reference composed by a diode and a resistor providing a 0.7 volts reference. This type is also called shunt-type regulator. Although the reference is decoupled by the raw supply, it has many deficiencies. Among them, the load current must always be lower than the driving current ID. The other important limitation is the negative thermal coefficient of the PN junction. All the transistors had a PN junction voltage of 0.7 volts and a thermal coefficient of negative 1.9 mV over Kelvin degrees. This means that keeping constant the current in the transdiode, the base emitter voltage decreases of 1.9 mV every degree. Another shunt regulator is this, where a Zener diode is added to the previous diode D2. The Zener diode has a fixed reverse avalanche breakdown voltage, and when this is set between 5V and 8V, its positive thermal coefficient compensates the negative thermal coefficient of the diode D2. With proper bias current in the diodes, we can reach a thermal coefficient of 100 parts per million per degree Kelvin. Since the best thermal compensation is at odd voltage level, the accuracy is limited. The load is also limited since the bias current must be carefully controlled. Moreover, references based on low TC Zener diodes also tend to be noisy due to the basic noise of the breakdown mechanism. A better circuit for stable voltage reference is this, based on the bandgap reference firstly described by Widlar in his paper, Some Linear Design Technique for Linear Integrated Circuit, in 1965. The idea is to compensate the negative thermal coefficient of the VBE junction, called CTAT, with the positive thermal coefficient of the delta VBE, called PTAT. The difference of the two VBE junctions operating at different currents is this, and you can see it is directly proportional to the absolute temperature. So the reference voltage is composed by the VBE of Q3 with a negative thermal coefficient plus the term R2 over R3 delta VBE, which has a positive thermal coefficient. By imposing the condition that the derivative of Vref with respect to temperature is 0, we get that R2 over R3 times log n has to be equal to 21.8. So Vref, to be thermally compensated, has to be equal to 1.25 volts. I leave a link in the description about bandgap reference. However, the basic design suffers from the load and current drive sensitivity, plus the fact that the output needs accurate scaling to more useful levels, i.e. 2.5 volts or 5 volts. The bandgap reference technique is attractive in IC designs because the relative simplicity and the avoidance of Zeners and their noise. Regulators can be seen as voltage reference capable of supplying a lot of current. Back in the early 70s, digital systems were spreading out. According to Widlar, they had a relatively high current requirements, but there was a number of problems associated with using one centrally located regulator. Heavy power buses must be used to distribute the regulated voltage. With low voltages and currents of many amperes, voltage drops in connector and conductors can cause an appreciable percentage change in the voltage delivered to the load. This is aggravated further with TTL logic, as it draws transient currents many times the steady-state current when it switches. These problems have created a considerable interest in on-card regulation, that is, to provide local regulation for the subsystem of the computer. Rough pre-regulation can be used, and the power distributed without excessive concern for line drops. The local regulators then smooth out the voltage variation due to line drops and absorb transients. So, for example, we can have an unregulated centrally located power supply of 15 volts and many stable and accurate 5 volts on-card regulators. Here you see a basic 3-terminals regulator with 6 volt as an unregulated input voltage and 5 volt as a regulated output voltage. The load current is 1 ampere and has to be much larger than the ground or quiescent current. If we consider the input current equal to the load current, we can say that the power dissipated by the regulator is this, and it is as much smaller as the voltage drop, V in minus V out, is smaller. Nowadays, this voltage drop is very low, but at the time this wasn't a concern. In the late 60s, the problem was integrating the power transistor into the die of the regulator to get a monolithic regulator. Back then, monolithic regulator didn't include the power transistor, which was externally driven by the regulator. The power element, provided of a special package for the heat dissipation, was able to deliver high current to the load. The power transistor, also called passive transistors in this case, is in series with the positive side of the unregulated input. The industry didn't believe in the possibility to include the pass transistor in an integrated circuit regulator. Even Widlar, in the paper Designing Positive Voltage Regulators of June 1969, writes against it. First, there are no standard multi-lead power packages, he said. For example, the LM100, an adjustable voltage regulator, had 8 pins and there wasn't 8-pin power package. Second, integrated circuits necessarily have a lower maximum operating temperature because they contain low-level circuitry. This means that an IC regulator needs a more massive heat sink. Third, the gross variation in chip temperature due to the dissipation in the pass transistor worsen load and line regulation. It looked a case closed, but in the February of 1970, in another paper, Widlar introduced its LM109, the first high-power monolithic regulator. It had just 3 pins, so it could be inserted in an ordinary transistor power package. It was designed for a logic card, so it provides a fixed 5-volt output and accepts input voltages from 7 volts to 25 volts. Considering the temporal proximity of the two papers, some say it was a joke, or most likely, Widlar wrote against the case of the integrated pass transistor just to discourage competitors from doing so. In any case, he was the first to make coexist the high dissipation of the pass transistor and the regulator circuitry, introducing thermal protection alongside the bandgap reference. In another paper of 1971, New Development in IC Voltage Regulator, Widlar wrote, "Thermal protection limits the maximum junction temperature, providing a constant power limit that protects the regulator regardless of input voltage, type of overload, or degree of heat sinking. With an external pass transistor, there is no convenient way to sense junction temperature, so it is much more difficult to provide thermal limiting. Thermal protection is in itself a very good reason for putting the pass transistor on the chip." When a regulator is protected by a current limiting alone, it is necessary to limit the output current to a value substantially lower than is dictated by dissipation under normal operating conditions, to prevent excessive heating when a fault occurs. Thermal limiting provides virtually absolute protection for any overload condition. Hence, the maximum output current under normal operating conditions can be increased. This tends to make up for the fact that an IC has a lower maximum junction temperature than discrete transistors. Additionally, a 5-volt regulator works with a relatively low voltage across the integrated circuit. Because of the low voltage, the internal circuitry can be operated at comparatively high currents without causing excessive dissipation. Both the low voltage and the larger internal currents permit higher junction temperatures. This can also reduce the heat sinking required, especially for commercial temperature range parts. Now let's see the general block diagram of the regulator. We have three terminals, the unregulated input, ground, and the regulated output. We have a voltage reference symbolized by a Zener diode, but we'll see the 109 uses the bandgap reference. The current on the reference device has to be carefully controlled. The reference is scaled to the output through the factor 1 plus R1 over R2. Every variation of the outputs is noticed by the error amplifier, which in turn controls the pass transistor, making it providing more or less current, creating a negative feedback, which stabilizes the output voltage reference. Additionally, we have the current limit and the over-temperature sensor, which control the pass transistor when current or temperature are too high. Now let's see the schematic of the LM109. First, we recognize the output voltage reference. We see Vout is equal to VBE10 plus VBE9 plus R8 times I7 plus VBE12 and VBE13. We have 4 base emitter junctions and the resistor R8 in which must flow a PT80 current. We need for every base emitter junction a PT80 voltage, such that the sum of the latter with the VBE is 1.25 volts. Having 4 VBEs, for thermal compensation, Vout must be 1.25 volts times 4 equal 5 volts. The PT80 voltage is, of course, RA times I7 and must be equal to about 2.2 volts. But this PT80 voltage is created by I7, which must clearly be a PT80 current. The current I7 is created by the voltage drop on R6 in this way: VBE5 plus VBE4 minus R3 times I5 minus VBE6 minus VBE7 equals to around 2 delta VBE. This voltage drop is produced by the difference of two base emitter junctions with high density of current, VBE5 and VBE4, and two base emitter junctions with a low density of current, VBE6 and VBE7. So this is a PT80 voltage, and dividing by R6 we get the PT80 current I7. Note that our PT80 voltage is not exactly a difference of VBEs, but we have also the R3 times I5 terms. So the drop on R6 is this. But we need R3 for a reason we are going to explain later. Note also that our PT80 voltage has a magnitude of 2 delta VBE. This improves the tolerance of the mismatch we cannot avoid in the device's production process. So this is the part of the circuit which provides the delta VBE. Here the error amplifier for controlling the pass transistor and creating the negative feedback to stabilize the output. Here the Darlington NPN pass transistor. At the time there weren't good PNP Darlingtons, so NPN was a forced choice. Of course, the NPN creates a dropout which affects the power dissipation of the regulator. Here the over-temperature protection. You see the transistor Q14 drives the pass transistor, drawing current from its base in case of over-temperature. Here we have the current protection circuit. In case of overcurrent, Q15 is turned on, drawing current from the base of the pass transistor, thus limiting the load current and protecting the load and the circuit. Here the collector FET that along with R1 ensures starting of the regulator under worst case conditions. Here the compensation capacitor to stabilize the negative feedback without the need of an output capacitor. Another protective feature of the regulator is the crowbar clamp on the output. If for some reason the output voltage tries to rise, D4 will break down and limit the voltage to a safe value. Moreover, if the input voltage tries to reverse, D1 will clamp this for currents up to 1 amps. Let's see the startup circuit. When we apply the raw voltage V into the circuit, the drain of the FET goes high and Q1 turns on, making current flow in Q4. Because of the working of the FET, the maximum current is just when the voltage between gate and source is zero, so a current biases Q4, turning it on. A voltage rises on R4 and when it reaches 0.7 volts, Q5 turns on. A current I5 is created and this current initially flows through R1, turning on Q3 and Q2. The collector of Q2 is the input of the current mirror composed by Q17, a PNP lateral multi-collector BJT. Q17 copies this current and spreads it, biasing the whole circuit, in particular the error amplifier and the Zener diode D2. Now, let's see the circuit producing the PT80 voltage on R6. We said the Widlar used two base emitter junctions at high current density, VBE4 and VBE5, and other two base emitter junctions at low current density, VBE6 and VBE7. So, let's see the currents. I4 is equal to 0.7 volts divided by R4, so 1.2 kilo ohms, equals 0.58 milliamps. I5 is equal to Vout minus VBE2 minus VBE3 minus VBE4 minus VBE5 divided by R2. So I5 is Vout minus 0.7 volt times 4 divided by 2.4 kilo ohms. I6 is the current flowing in Q6 and it is equal to VBE5 plus VBE4 minus R3 times I5 minus VBE6 divided by R5, but R5 is 12.1 kilo ohms, 10 times R4 because we want I6 10 times I4. VBE4 and VBE5 are 0.7 volt each, but VBE6 is a little less than 0.7 volts because the current I6 has a low current density, so 1.4 volt minus VBE6 is a little more than 0.7 volts, but this is compensated by the R3 I5 term to reach a numerator of 0.7 volt. At the moment, let's say just VB6 is 0.7 volt, so I6 becomes this as function of Vout. The current in Q7 is equal to Vout minus VB13 minus VB12 minus VB9 minus VB10 divided by R8, which is 24 kilo ohms. So I7 is this, which is equal to 1/10 of I5. So you see I5 is 10 times I7 and the I4 is 10 times I6. As you see, currents at higher density flow in the base emitter junctions VB4 and VB5 with respect to VB6 and VB7. So now, knowing the current as function of Vout, we get Vout, but first let's recall the voltage dropping on R6. It is equal to VB4 plus VB5 minus VB6 minus VB7 minus the voltage drop on R3, which is R3 times I5. This can be written in this way, assuming the 4 transistors matched. So I7 is also equal to this. Now we remember that Vout is equal to VB10 plus VB9 plus R8 times I7 plus VB12 plus VB13. So it is equal to 2.8 volts plus R8 times I7. Putting all the currents inside the formula, we get this equation as function of Vout. We can solve this equation in iterative way and get Vout equals 5.1 volts. This is an approximation. The real value is 5.05 volts. Anyway, we got that the output voltage is 5 volt and this means that the 4 VBEs are thermally compensated. Knowing Vout is easy to find the 4 currents. We already know I4 and we get I5 equals 0.94 milliamps. I6 is about this, keeping our approximation, and I7 is this. Knowing I7, we can check the value of I7 times R8, which has to be around 2.2 volts to compensate the 4 base emitter junctions. We get 2.256 volts, which added to 2.8 volts gives a Vout of 5.056 volts. So the reference circuits provide the bias needed to create the delta VBE on R6, which in turn creates the PT80 currents I7 needed to create the PT80 voltage on R8 and compensate the 4 base emitter CT80 voltages. So we have seen how we create a PT80 voltage on R6, but we should remember that on R6 we create a delta VBE less R3 times I5. So why Widlar introduce R3? Let's say the output voltage has a little variation. Part of this is propagated to the base of Q4. Without R3, the base of Q4 and Q6 are directly connected, so we have the same delta V on the base of Q6, introducing an error on the delta VBE produced on R6. But with R3, things change. The delta V reaches the base of Q6 in two ways. The first way is through R3. So on Q6 we have this voltage divider, and because R05 parallel RPi6 is much larger than R3, the delta V passes unchanged to the base of Q6. The second way is through Q4. The delta V passes unchanged on the base of Q5 because the parallel of RPi5 and R4 is much larger than 1 over GM4. So on the base of Q6 we also have negative GM5R3 delta V along with the delta V. So the total voltage on the base of Q6 is this. GM5 is equal to this and R3 is 25 ohms, so the variation on the base of Q6 is this, which is much less than delta V. So we can say R3 is introduced for compensating the transconductance of Q5 and decoupling as much as possible Q6 from the variation of the output. Now let's see the error amplifier working. If for some reason the load current provided by the pass transistor raises and Vout goes above 5 V, a delta V is produced. This delta V reaches this node almost unchanged because Q12 and Q13 have little resistances. The delta V reaches the base of Q9 almost unchanged because the resistance seen from here is this and is much more than R8. Q9 is an emitter follower and it lets pass the voltage on the base of Q10 in common emitter configuration. Q10 produces this current and Q11 draws current from the base of the pass transistor. So Q11 acts as buffer, providing a little resistance for the current. Taking current from the collector of Q17, we prevent it to go to the base of the pass transistor, thus reducing the load current and pushing back to 5 V the output voltage. So a negative feedback is acting, and because we want this feedback negative, we add a compensation capacitor. I leave links in the description about negative feedback and compensation capacitor. The error amplifier has one more feature. You see on R7 we have a PT80 voltage given by the difference of the base emitter junctions of Q10 and Q8. So when the temperature raises, the collector current of Q9 raises as well, drawing current from the pass transistor. This behavior compensates the increasing current in the pass transistor due to the temperature increase. The pass transistor is an NPN Darlington introducing a significant dropout. The input voltage range is between 7 V and 35 V, so the dropout is at least 2 volts. In the late 60s, PNP Darlingtons were poor, so if you needed a power transistor, you were forced to use a NPN and tolerate the dropout. The pass transistor can provide currents above 1 ampere and it is very large, larger than the rest of the circuit. As we said, the real innovation of the circuit is the presence of the power transistor in the chip, and this has been possible because of the presence of the thermal protection circuit. So let's see the thermal protection circuit. One of the collector Q17 provides bias current to the D2 Zener diode. So 6.3 volts drop between the base Q16 and an end of R10 resistor. In this way, we give around 300 mV on the base emitter junction of Q14. The base emitter junction of Q14 is the thermal sensor. At 300 Kelvin, 320 mV is not enough to turn on Q14, but if the temperature raises, the base emitter junctions of Q14 decreases of 1.9 mV every degree. The thermal coefficient is this. To turn on, the base emitter junction needs around 0.6 volts at 300 Kelvin, around 27 degrees Celsius. But as the temperature raises, the voltage at which Q14 turns on decreases by 1.9 mV for every degree. So at 175 degrees Celsius, corresponding at 448 Kelvin, the switching voltage is 390 mV, and it is equal to the fixed 320 mV dropping on R10. So at 175 degrees Celsius, Q14 turns on, drawing current from the base of the pass transistor. Due to the fixed 320 mV voltage on the base emitter of Q14, as the temperature increases above 175 Celsius, the current IC4 increases rapidly, drawing more current from the base of the pass transistor. The thermal protection is an overall protection. When the current raises, the temperature also raises. However, in order to prevent secondary breakdown in the pass transistor, a current protection circuit is added. Secondary breakdown is a critical failure mode in power transistors that can lead to catastrophic device failure. It leads to sudden and uncontrolled current spikes, creating hot spots and damaging the device. When the output current increases, a voltage drop is created on R14. When this voltage drop reaches 0.7 volts, Q15 turns on, drawing current from the base of the pass transistor, thus limiting the load current. The output current is limited to this value. Moreover, if Vin minus Vout, so if the dropout voltage is more than 7 volts, this branch is activated. A current flows in R12, creating a voltage drop. In this way, you need less current on R14 to turn on Q15, thus making the load current limit less than 2.3 amps. Here you see a photomicrograph of the regulator chip. It shows that high current pass transistor on the right takes more area than the control circuitry on the left. It can be seen that the pass transistor, which must handle more than 1 amp, occupies most of the chip area. Please leave me a comment and let me know if you liked this video. Make sure you put a thumb up, click the notification bell and subscribe to my channel.